Hello students, in physics in the section heat, we are going to see another experiment now. What is this experiment? This is about the determination of relative humidity of air using a polished calorimeter. So when I say determination of relative humidity, let's try to understand or let's try to recall what is relative humidity. We studied earlier in theory, relative humidity means if you take a unit volume, what's the meaning of unit volume? Take 1 meter width, 1 meter length, 1 meter height, cubic area, then I can say 1 meter cube, cubic area. 1 meter cube is the volume. In that volume, how much of vapor can be contained? Basically, the maximum amount of vapor that can be contained. Why there is a maximum? Because when the vapor concentration increases within that unit volume, beyond a point, that vapor, because they don't have enough space, when see from liquid state to vapor, when they move, their mobility increases, their energy increases. So they need more space to move around. When you keep adding vapor into a confined space, when the concentration of vapor increases, beyond a point, beyond a certain concentration, the space won't be enough for them. Then what happens? They will start condensing and they will change the state into water. Right? That's what we call dew point. So, the maximum amount of vapor that can be contained within a space. First, we need to understand that. Then, at a given moment, at this moment, how much of vapor is existing in that unit volume? The ratio between those two is what we call relative humidity. Let's say in a room, right, in our lab, altogether in that space, let's say 10 kilogram of vapor can be contained. That's the maximum. Right now, at this temperature, at this pressure, let's say there is only 4 kilogram of vapor in the air. With the air, there will be some amount of vapor already mixed, which may not be the maximum, which is not usually maximum. It's below the maximum level. So when the maximum vapor that can be contained is 10 kilogram, let's say currently, right now, there is 4 kilogram in the air. Then I can say the relative humidity is 40%. You multiply this by 100 to get the percentage. So 40% is the relative humidity of this space. So what is relative humidity? The availability of vapor in the air as a percentage of the maximum vapor that can be contained or that can be contained in the air. That's what relative humidity. To find relative humidity, there is another formula. What is the other formula? This is it. Saturated vapor pressure at dew point divided by saturated vapor pressure at room temperature into 100. This also we will be studying in theory. How this has come and all we will study. So first understand what is dew point. Now in this room, right, in the lab, already in the air there is a certain amount of vapor. Now we say that is not the 100% of vapor capacity in this room. It's below. As per this number I have put, it's 40%. Now what will happen if I keep reducing the temperature? When the temperature reduces, the maximum amount of vapor that can be existing, that can be contained in this air, the maximum limit will start falling down. When temperature drops, that maximum also drops. So let's say now the room temperature is 30 degree. At 30 degree, if 10 kilogram can be contained, when you bring it down to let's say 26 degree, it may not be 10 kilogram. It might come down to 7 kilogram. Not a linear relationship. Understand, when the temperature drops, maximum amount of vapor that can be contained in that air also will drop. When it comes to let's say 22 degree, let's say this has come to 4 kilogram. Now look at this. There was already 4 kilogram available, right? Now the maximum is also 4 kilogram, right? Which means at this temperature, they have marginally, they are packed inside. They don't have excess space. You can't include more vapor into it. Now what will happen? Temperature drops by even 0.1 degree after this. Now it's 22 as per these numbers. If it drops by another 0.1 degree, then the maximum capacity of vapor in that space is going to be less than 4 kilogram. But already 4 kilogram of vapor is inside. Then what will happen? The vapor will start condensing. Which means at that point you will see dew forming on the surfaces. Whichever the surfaces, you will see the vapor will get condensed. If it is walls, on the walls you can see some mist. If you have a glass, on the glass you can see some mist. What is that mist? Vapor gets condensed. Which means according to these numbers, 22 degree, I can say that's the dew point. But the room temperature was 30 degree, right? This is the room temperature. Room temperature and dew point. Do you understand what is meant by dew point now? Right. So what this formula says is, at the dew point, saturated vapor pressure, and at the room temperature, saturated vapor pressure, get the ratio between those two. Get the ratio between those two and multiply by 100, that should give you the relative humidity. So what we are going to do in this experiment is nothing much, finding the dew point. Because if we know the temperatures, at each temperature what is the saturated pressure, there are tables or graphs. We can use the graphs, we can use the tables and find, okay, at 22 degree what is the saturated vapor pressure. At 30 degree what is the saturated vapor pressure, we can find that. We can find that. Right, saturated vapor pressure depends only on temperature, only on temperature. So if you know the temperature, you can find the saturated vapor pressure. There are standard tables for it. So all what we are going to do in this experiment is finding the dew point first. Clear? How we find dew point is very simple. You take a calorimeter or a metallic container with polished surface. Usually we will have two identical containers. In one you fill some water and keep the thermometer in the middle. Add some ice cubes, small ice cubes or ice chips one by one and keep stirring it to reduce the temperature. So when the temperature reduces, at some point you will see mist forming on the surface of that calorimeter. That temperature is going to be the dew point as per this explanation. That temperature, the temperature at which dew forms. Then why do we have another calorimeter? Just to compare and see. Because otherwise you will not really notice at which point the dew forms. So you have one calorimeter which we did nothing on it, that remains polished forever. The other one has water and we are adding ice chips into it. So at some point this is getting dew on its surface, dew deposits. Then when the dew deposits are there on the surface, the polished surface will start becoming, it will get tarnished. It won't be polished. Right. So then you can compare, okay, one is remaining polished, okay, this is becoming tarnished. Find the temperature at the moment when it becomes tarnished. And also then we continue the experiment, we don't stop there. To get the precise dew point, what we do, then we don't add, after it gets tarnished, we stop adding ice cube, keep stirring it continuously. Then what will happen? Since we are not adding ice cubes, it will start gaining heat from the environment and the temperature will start going up again. When the temperature starts going up, then we are going to come above the dew point, right? When whatever the dew formed will get vaporized again. So find the temperature when the dew formed starts vaporizing. That means the tarnished surface when it becomes polished again. Note that temperature. So already you found the temperature when it got tarnished. Now from tarnished surface to polished surface, when it changes, again get the temperature. Get the average of both those temperatures. That will give you the precise dew point. That will give you the exact dew point. So once you have found the dew point, then go to the table. Take your table or chart. On the chart, You can read, okay, my dew point is this many degrees and this is the saturated vapor pressure. My room temperature is this many degrees, this is the saturated vapor pressure. Get those two values, substitute here, multiply by 100, you get the answer. Relative humidity. Clear? That's what the concept is. See what materials and apparatus we need for this? 2 calorimeters with polished outer surfaces, sufficient amount of ice chips, a stirrer, 0 to 50 degree thermometer. Why 0 to 50? Because if the room temperature is 30, all your experiment is going to be below 30 because you are going to add ice cubes into that. If room temperature is 35, we won't go beyond 35. It's going to be below 35. Therefore, you don't need 0 to 100 thermometer. 0 to 50 is more than enough for you. A sheet of glass. What are we going to do with a sheet of glass here? Now see, when you are doing the experiment, let's say I keep the calorimeters like this on table. I stand here and I do the experiment. Then in front of calorimeter, I'll be breathing. So my exhaled air, when I am breathing my exhaled air, usually exhaled air has more vapor content than the room air. Then what will happen when I am exhaling, when I am breathing the exhaled air, if it falls on the calorimeter surface, since it has more vapor in it, I told you like see in this number, when temperature drops, the maximum vapor that can be contained also drops, right. So what will happen, see usually if the percentage is 40% in the air, when I breathe, my exhaled air is going to have more percentage of vapor. Then what will happen, it won't wait until 22 degree, even at 27 degree, 28 degree, at a higher temperature, the mist might start formed. Right, on the calorimeter surface, even before the dew point of the room vapor content, you might be able to see vapor because my breathing air, exhaled air falls on the calorimeter. Exhaled air has more vapor content than the room air. So we have to prevent this. We should not change the composition of the room air. So what do we do? In between the calorimeters and me, the person who is doing the experiment, in between those two, we keep a glass sheet. It has to be a transparent sheet because I have to see what happens on the other side. But it should not allow my exhaled air to fall on the calorimeter. So take a glass sheet which is large enough to prevent the exhaled air of the person who is doing experiment to fall on the calorimeter. That has to be prevented. That's why we have this sheet of glass. So usually you keep the calorimeters, then you take 2 stands. With the stands you fix this glass, right? On this side of the glass you stand and do the experiment. So to separate the person who is doing the experiment and the arrangement, you keep a glass sheet. And 2 stands are to fix the glass sheet. Clear? This is all the materials. Let's see the method. Wipe out well the outer surface of the calorimeters and fill about a half of 1 calorimeter with water. Approximately half, not exactly, it has to be half. Why we fill it with half? Because you have to add ice cubes and stir it, right? So to keep enough space to add ice cubes, we say usually up to half, right? Not a hard and fast rule. Even if you add a little bit more, it is not going to make much difference. Fix the sheet of glass in front of the calorimeter to prevent your exhaled air reaching the calorimeters. Insert ice chips into water in the calorimeter one after the other, while stirring each one after the previous one has dissolved. Now this is important. If you suddenly add a big cube, or if you add lot of ice chips at once, what will happen? Suppose if your dew point is 22 degree, if you have added lot of chips, at once the temperature might go to a much lower point. Say temperature reaches 15 degree. understand, for any temperature below the dew point, you will see dew. So, suddenly temperature has gone down to 15, now you see dew, you might think 15 is the dew point, which is not the case. You have quickly passed the dew point and you have gone below that. That's why we say add the chips one by one and slowly, say if you are at 30, check 29, no dew, check 28, no dew, 27, no dew. One by one, slowly you have to go down one by one in temperature to find out what is the dew point. And there is another problem. If the temperature drops far below the dew point, then you won't see mist. Instead of mist, what you will see is larger water drops. I'll tell you an example. See, you have a cool drink bottle, a glass bottle with cool drinks in the fridge. Fridge temperature is usually say 15-16 degrees, which is usually below the dew point, much below the dew point. You take that glass bottle with cool drink and keep it outside. What will happen after a few seconds? You will see a lot of water drops, not just the mist. Larger water drops will be formed on the outer surface of that bottle. So what? Nothing wrong. The problem is then later when the temperature increases, we expect the dew to vanish, right? And we expect the polished surface to return, which won't easily happen if the water drops are big. If you have a thin layer of dew, then that will nicely get vanished quickly. But if you get bigger water drops, it won't vanish easily. So because of these reasons, you have to add small ice chips one after the other. Observe the beginning of tarnishing of the calorimeter surface due to depositing of dew by comparing the surface with the outer surface of the other calorimeter. Just for comparison purposes only, we have the other calorimeter. In the situation where dew begins to deposit, observe and note down the reading θ1 of the thermometer. Now stop adding ice and continue stirring to allow the temperature of the water to rise when the shine of the calorimeter begins to reappear, indicating the vanishing of dew. Observe the thermometer reading θ2. So θ1 plus θ2, like the dew point is going to be θ1 plus θ2 by 2. That will be the dew point. θ1 is the temperature when the dew forms, when the shininess of the outer surface vanishes, right? When the surface gets tarnished, θ1. θ2 when it returns, that means when the dew vanishes, when the shiny surface returns, right? Finally, observe and record the room temperature, θr. So you got the dew point like this, you got the θr. For the dew point, you find the saturated vapor pressure. For θr, you find the saturated vapor pressure. Let it be P naught, let it be P naught by P into 100 is going to give us the relative humidity, right? So that's a very simple experiment, Let's see how we are going to do it in the laboratory. The apparatus required for this experiment include two identical calorimeters with shiny outer surface. I already explained you why it has to be shiny, because then only we can observe when the mist is formed around on the surface of calorimeter. And one has to have a stirrer. You can see we are using a stirrer here. Yes, because when you are adding ice cubes, you have to keep stirring it. The main reason is the temperature we are going to measure is of the water, whereas the dew point is actually the surface temperature, outer surface temperature. How do we ensure that outer surface temperature and the temperature we measure inside the water are equal? If you keep on stirring it continuously, that will ensure it. So we need a stirrer, and then we need a thermometer to measure the temperature when the dew is formed. When the surface become blurred, we should check or we should measure the temperature. For that we use a thermometer. Water, we will be filling this calorimeter with water, and within water only we will be adding ice cubes. When you are filling water, do not fill it to half or for a less quantity of this calorimeter. Fill as much as possible, leaving a little bit of space to add the ice cubes, because if you fill it to a lower level within the calorimeter, then the entire surface will not be with the same temperature. The level up to which water is there will have the water's temperature. Above that, it will be a different temperature, which will be an error in the experiment. So, make sure you add water close to the full capacity of the calorimeter, leaving maybe 1 centimeter space, 1 centimeter below the top, just to add the ice cubes into that. These are the ice cubes we are going to use. One by one, we will be adding the ice cubes, and we will check whether the outer surface is getting blurred or not. Additionally, we are using a glass. Can you see a piece of glass, right? What we are going to do with this glass, when we do the experiment, in the breath, there will be vapor. So, if the breath directly falls on the calorimeter, the water content in the breath will get condensed on the calorimeter, and because of that there might be mist forming. To prevent that, in between the person who is doing the experiment and the calorimeter, a glass piece will be kept, so that the breath and the water content in the breath doesn't reach the calorimeter directly. It falls on this glass which we keep in between, right, which is an important step, important measure in this experiment. Otherwise, when we are breathing, when we are talking, that will have water content that will get condensed on the calorimeter surface. So, to hold this glass, we will be using a stand like this. So, that is all the apparatus and materials we require to do this experiment. Now, we will see how we are going to do this experiment. So, now you can see the arrangement to do this experiment. I have fixed the thermometer within the calorimeter, right. So, as I mentioned earlier, let us add water into this. Leaving some space for adding ice cubes. I have filled it approximately 1 centimeter below the top. I have added water. Now, what we will do? Let us add the ice cubes one by one, and comparatively I have to see. Now, you can see both calorimeters are shiny. Both have outer surface shiny. This is shiny, this is also shiny. Both of them are shiny, right. What will happen when I am adding ice into this? This will start losing its shininess, right. This will become more blurred. That is what we are going to observe, right. So, let me add the ice cube first. Make sure you add one ice cube at a time. After it melts, check whether the surface is not yet blurred, and then you add the next one. Also ensure this glass is fixed in between the person who is doing the experiment and the calorimeter, right. Now, let me keep stirring it. I can see the temperature is going down. It has come down to 25 degrees now. Now, it is 24. Let us add another ice cube. Let us keep stirring it. After this ice cube melts, you can add the next one, and also keep watching the outer surface of both calorimeters compared to the one without water. The one with water should become blurred. The moment it becomes blurred, it turns to be, or it starts to lose its shininess, we will say the dew is being formed. Then we can check the temperature at that point. Temperature has gone down now, it's going below 22 now. Let me add another ice cube. Temperature has gone down to 19 now, 19 degrees. Still I don't see much of a difference, I don't see any difference on the outer surface. Now it has gone down to 18. Let's add another ice cube now. Let me check the previous one is melted. Yes, let me add another one. It's going below 18 now. Now the temperature is approximately 17. Still I don't see any difference. It's going below 17 now. Students, now you can see the temperature is 16 here. 16 here, the temperature is 16. At 16, the surface is getting blurred. Can you see it starts to lose its shininess, right? Compared to the other one, now it's starting to lose the shininess. Right, which means at this point when the temperature is 16 degree, the dew is formed on the outer surface of this calorimeter, right, which means the dew point is 16 degree. But as I mentioned earlier, we are not going to stop the experiment at this point. We will just leave it like this. Now what will happen, the calorimeter and water content will get the heat from environment. When it obtains heat from the environment, the temperature will increase. When it increases, slowly at some point, the dew that is formed on the outer surface will start vanishing. So the moment it starts vanishing, I have to check the temperature again. So this 16 and that temperature, the average of those two will give me the dew point. Right. So let's wait now. Let's keep stirring and see at which point this the dew that is formed starts to vanish and the calorimeter starts to gain its shininess. Let's check that now. Students, you can see now look at the surface here. This is very shiny. Can you see? This one is shiny. It still remains shiny. Whereas look at this one. It's not as shiny as the other one, which means the dew is being formed here. This is what we said, the calorimeter, when it starts losing its shininess, the dew is being formed, right. The temperature now is the dew point, which is 16 degree. Now let's wait until the temperature goes up and see at what point the dew starts vanishing. Students, now you can see when the temperature is increasing, now it is at 17, can you see? Now it is at 17. At 17 degree, the dew that was formed on the outer surface starts vanishing. That means the surface is becoming shiny again, right. So the temperature at which the dew started to form is 16. The temperature at which the dew started to vanish is 17. Let's get the average of both, 16, 17, average of both. 16.5 degrees will be the dew point, right. Now for the 16.5 degree, I can use the table, the dew point versus the relative humidity table is there. There I can find at 16.5 degree dew point what would be the humidity, relative humidity. But to find that, I need to know the environmental or the room temperature also now. So now what we will do, let's check the room temperature. Students, the room temperature now, it is at 29 degrees centigrade. It remains stable at 29 degrees. Room temperature is 29 degrees centigrade. So, at 29 degree room temperature, 16.5 degrees was the dew point. Now, we can use the table as I mentioned earlier and find out the relative humidity of air. Let us see how we can find that. Students, you can see the readings we have got. Temperature at which dew deposits 16 degree, when dew vanishes it's 17 degree. So, dew point has to be 16 plus 17 by 2, which is 16.5 degree. Then we can find the saturated vapor pressure at this temperature, at dew point. You can use the table and find it. It's 18.77. And then room temperature 29 degree. So, the pressure, saturated vapor pressure at room temperature is 40.05. 40.05. Now, what do you do? P naught by P, relative humidity, the saturated vapor pressure at dew point divided by saturated vapor pressure at room temperature into 100. That is 18.77 divided by 40.05 into 100. So, you get approximately 4416, 27, 46, 24, 37, 9. 46.9 percentage is the relative humidity you are getting, right? That is the relative humidity. Clear? So, it is very simple, straightforward calculation, there is no complication as such. Now, let us see some questions from past exam papers. See, I have taken 2003 past paper for you. You are required to determine the dew point at laboratory using a polished calorimeter. What experimental procedure would you follow to get dew deposited on the calorimeter surface? What did we do? We filled the calorimeter with water and we were adding ice chips one by one. Let us write that. Fill the calorimeter with water and add ice chips one by one. That is how we got to the dew point. Next, what are the two temperature readings you have to obtain in this experiment? One when the dew is being formed and the other one when the dew starts vanishing. We will say one, the temperature when dew starts to get deposited on the calorimeter surface, calorimeter outer surface, and it gets tarnished. It gets tarnished. Other one, the temperature when dew starts to vanish and the shine of the surface reappears. Right? Those are the two temperature readings we get during the experimental procedure. Then at the end we have to get the room temperature also. Next. Water is stirred in this experiment to maintain uniform temperature throughout the volume of water. Why is this important? Why are we keep on stirring water? Now see, what is going to be the dew point? The temperature on the outer surface. When dew forms, what temperature, which temperature I actually have to measure is the calorimeter's temperature. But you can't keep the thermometer on the calorimeter surface because the thermometer's bulb has to be completely covered by the substance. So you can't just go and keep it on a surface. Right. So how do we measure the surface temperature? We assume the temperature of water within the calorimeter and the calorimeter surface temperature are equal. We make an assumption like that. For that assumption to be valid, you have to keep stirring it. When you are stirring only, this assumption becomes valid. What assumption? The temperature of water and the temperature of calorimeter outer surface are equal. To ensure that only we are stirring it. To ensure the temperature of water and calorimeter surface temperatures of water and calorimeter outer surface are equal. For this only we keep stirring it. We have done that in other experiments also, you know that. If the two temperatures obtained in B above are 23.2 and 23.6, what is the dew point? Dew point equals 23.2 plus 23.6 by 2, which is 23.4 degrees centigrades, 23.4. Dew point is 25 degrees on a day when the room temperature is 30. Assume that relative humidity has to be determined using the following temperature versus saturated vapor pressure chart. Right. So we are talking about 25 degree. Let's mark that on the graph. Anyway, we will need it. 25, 25, 20, 25. Mind you, this is a graph that has been reproduced from your exam. So there might be small deviations between this and the actual graph that was given in the exam. Okay. I will do calculations as per what this graph shows me. Sometimes there can be marginal differences, slight differences between this graph and what was given in the actual exam. So don't look at the final answers, but look at the method, how we do it. That's what is more important, because they won't give the same numbers again. They can give this question with different numbers next time. If we check here, 30, it's approximately 35. The saturated vapor pressure is 35 millimeter mercury. And here, this is also quite close to 25. 25. Write down the formula that you use to find the relative humidity. Equals saturated vapor pressure at dew point divided by saturated vapor pressure at room temperature into 100. Hence, find the relative humidity. (25 divided by 35 into 100, isn't it? This is the dew point, at that it's 25. 25 divided by 35 into 100. 575, 500 by 7. 7, 7, 49. Then you have a 10, 7, 30, 20, approximately 3. 71.43 percentage is the relative humidity we get. 71.43. Very easy. It's very easy. There's nothing, no complication at all. When you blow your exhaled air on a polished metal surface, it is seen that the metal surface tarnishes. Explain why. Why? See, when we, like in the normal room temperature, the content, vapor content in the air within the room is not saturated yet. But when I am blowing, the exhaled air has more vapor content. So that might be saturated as per the room temperature. That's why it condenses on the surface. So what you have to highlight here, the exhaled air has more vapor content. The concentration of vapor is high. So let's write that. In the exhaled air, concentration of vapor is higher than that in the room air. Therefore, it condenses at higher temperature also. At higher temperature than the dew point of the room air. Because of higher concentration of vapor, it condenses, it forms dew even before the dew point of the air in the room. So basically, the air in the room has low vapor, so its dew point is lower. The exhaled air has more vapor, so its dew point is higher. So when I am blowing, even at room temperature, it reaches the dew point and the vapor is formed. Look at this one. This is another past paper, 1993. The following are given to you to determine the relative humidity of air in the school lab. A metal container with polished outer surface, sufficient amount of water and ice chips, stirrer. What else would you require to carry out this experiment? What is missing here? Thermometer is missing. Thermometer. That's the main one missing here. And maybe you can say a sheet of glass. A sheet of glass. Stand. Sufficient amount of water and ice chips is there. Yeah. Next. Draw a label diagram for the experimental arrangement of this experiment. Okay. So you have a calorimeter filled with water, and then you keep a thermometer, then you keep a stirrer. Let's name them calorimeter. Did they say calorimeter or metal container? They said metal container, so we'll also write metal container. Metal container. Metal container. Then this is water. Water. Thermometer. Thermometer. And a stirrer. You don't necessarily have to show the stand and the glass here, we can't show it. So that's enough. Next. What is the purpose of using a container with polished outer surface? Then only you can observe the formation of dew and the vanishing of dew. Otherwise, it's difficult. Imagine you take a surface, a container which already has a tarnished surface, which doesn't have a clear surface. Then, when the dew forms on it, you can't observe it. You will have to wait until a lot of water is formed. Then only you will see, yeah, there is water. We can't wait until then. The moment dew starts forming, I need to find it. So, to easily observe formation of dew and vanishing of dew. And vanishing of dew. What measurements do you take in this experiment and when do you take them? Same question they asked earlier also. The temperature of water when dew forms and surface tarnishes. That is one. And the other one will be the temperature of water. Temperature of water when dew vaporizes or dew vanishes and shine of surface reappears. See, similar questions, same questions they ask again and again, not even similar, same one. This was in 93, they asked that again in 2003. What is the benefit of adding ice chips one by one in this experiment? Why are we adding one by one? To ensure the dew point or the point at which dew starts to form can be easily identified. Otherwise, you can't. To precisely identify the first point at which dew starts to form. Dew starts to form. Dew starts to form. The first point, the first temp, or the highest temperature. First point means you can even say the highest temperature would be better. The highest temperature. Highest temperature at which dew starts to form. Because below the dew point, all the temperatures there is going to be dew on it. What we need is the highest temperature. When we are reducing the temperature from room temperature, when you keep reducing, what's the first instance you see dew? That's what we need. If the temperature of water drops significantly below the dew point, you will face difficulty in obtaining one of the readings. Explain why. I think I explained earlier. If you drop the temperature significantly below the dew point, then larger water drops will be formed on the surface. So what? When you increase the temperature, larger water drops won't vaporize easily. Right. So getting the second reading of temperature will be hard. Let's write that. Larger water drops will be formed. Why is that? Listen. Now earlier I said, I remember example, I said 30 degree, 10 kilogram can stay. 27 degree, just assume some example, 6 kilogram can stay. 22 degree, 4 kilogram can stay. Let's say already there is 4 kilogram. So in the next moment, say 21.9 degree, let's say it's 3.9 kilogram. So that 0.1 kilogram has to condense. Right? So you will get slowly the dew starts forming. What will happen? It goes to 20 degree. This may be 3 kilogram. Then what happens? Already we have 4 kilogram vapor in air, but you see only 3 kilogram that stay there, then 1 kilogram has to get condensed. More vapor has to get condensed, which means more water has to be formed. That's why I say if the temperature drops significantly, larger water particles, larger water drops will be formed. And they won't easily vanish then when you are increasing the temperature. Will be formed. This will not easily vanish. Therefore, taking the second reading of temperature, taking the temperature reading when dew vanishes is hard. That will be hard. Next. Dew point in a laboratory was 24 degrees centigrade when the room temperature was 30. Following graph shows the variation of saturated vapor pressure P in this lab against temperature theta. Remember again, this is a reproduced graph. If you take the original paper, sometimes the points can be slightly different, but look at the method what we are going to do. 24 and 30. 24 and 30. 24 is here. 30. I think this is 2.75 into 10 to the power 3. This is 4. What is the saturated vapor pressure at dew point? Dew point 24 degree. At that, saturated vapor pressure is 2.75 into 10 to the power 3 pascals. 2.75 into 10 to the power 3 pascals according to the graph I have. Calculate the relative humidity of air in this lab. Relative humidity, you know, P naught by P into 100. P naught 2.75 into 10 to the power 3. P is 4 into 10 to the power 3 here. 4 into 10 to the power 3 into 100. 10 to the power 3, 10 to the power 3. Then you get 4, 6, 24, 4, 8, 32, 68.75 is the relative humidity. So simple, very simple. So quite a simple experiment with not much of technicalities in it, not much of confusion in it, not much of complication in it. Very straightforward experiment, very straightforward calculations you have. Clear? So practice all this. Let's meet up again with another experiment.